All right, cool. Let's go ahead and get started. So welcome to the last lecture of computer architecture. Before we head on to Build Week, here's the agenda for today. As usual, we're going to go over the last part of the guided project. Make sure you guys know how to implement push and pop, because to implement this last part of the project, you guys need to have a solid understanding of how the CPU uses the stack. So after that, we're going to talk about subroutines or functions. Subroutines and functions are going to be synonymous, so they're the same, and how the computer deals with them. So, as you may know, a program has many functions. So how does the computer handle jumping in memory to execute those functions? So we'll talk about that today. After that, we'll talk about a stretch goal, which are interrupts. So what does a computer do when something happens? For example, the user moves the mouse or types a keyboard. How does the user handle that when it's executing a program? And how does it save the state and handle that interrupt so that once the interrupt is done being handled, it can go on and resume the program before it got interrupted? So those are interrupts. Stay tuned for that. Reminder, I will hold an AMA tomorrow, 6 to 7 p.m. Please be there on time. If no one's there, or if people run out of questions, I'm just going to end it early. Okay. Cool. So let's actually talk about the last part of the guided project. Your job was supposed to implement the system stack, basically implementing push and pop, and be able to run the stack LSA program. So I want to know from you guys, I want to gauge how you guys felt about that last part. Did you guys feel it was, give me some thumbs up, thumbs down, thumbs in the middle? Cool, I'm seeing some thumbs up, thumbs up, which is good. I'm seeing some nods, that's a good sign. So, okay, cool. So that's good that I'm not seeing any bad reactions. So what we're gonna do is we are going to go ahead and I'm going to explain to you guys my thought process and how I went about that part of the guided project, and also recap the things we talked about in the last lecture, just so that we're all clear on how that works, because you guys are going to need to know how this works in order to implement the next part of the project. So here is our CPU class that we've been chugging along in our past lectures. And here on the right is basically the stack program that you need to be able to run after you've implemented push and pop. So let's first talk about this file over here, and let's talk about what it's supposed to do. Let me start doodling. Okay. So in this program, you can see that we're going to need 3 registers, R0, R1, and R2. So I'm going to go ahead and initialize those registers right here so that you guys can visualize what the values of those registers are. And what we're going to do is we're going to run through and track the state of our program, just so that we know what it's doing. So we can also check our output once we actually implement it. So let's walk through this program. So in the first instruction, we have load immediate R0 with the value 1. So this is saying load R0 with the value 1. So I'm going to go ahead and do that. So the value of R0 is 1. Next instruction, load immediate R12. So R1 is going to have the value 2. And also here, we're going to start using push and pop. So let me go ahead and instantiate just kind of like what the stack looks like so that we can visualize it easily. Here's our stack. Our stack pointer is always pointing at the top of the stack. So we're over here, and then we're going to do push R0. And remember, push, what it does is it decrements the stack pointer, because remember, the stack goes downwards. It decrements the stack pointer and stores the value stored in this register onto the stack. So push R0 is basically saying push the value stored in R0 onto the stack. So to do that, we're going to decrement our stack pointer. Our stack pointer is now right here. And we're going to store whatever value is in R0, which is 1. Okay, so next thing, push R1. So push the value stored in R1 onto the stack. So we're going to do the same thing. We're going to decrement the stack pointer. And we're going to store 2 at the top of the stack because that is what it is in R1. And after that, we're going to do LDI R03. So load the value 3 in R0. So this gets overwritten with value 3. And then after that, we're going to pop R0. So this is saying pop the topmost element of the stack and store it into R0. So to pop at the top of the stack, what we first do is to get the element that is at the top of the stack and store it in R0. So now this is going to be 2. And then after that, we are going to increment the stack pointer, because we've popped it off the stack. So now the stack pointer is actually here. Okay. Yes, so now we are here at pop R0. I'm getting lost. I should probably start marking it. So we're here at pop R0. So now we're gonna print R0. So we should keep track of our output. Our output is we're gonna print the value in R0, which is 2. Okay, so our output is 2. So we were just over here. Now we're gonna do load immediate R04, so store 4 in R0. So over here. Then we're gonna do push R0, so push the value stored in R0 on top of the stack. So our top of the stack is over here right now. So to push, we decrement the stack pointer, so we're back up here. And then we write that value on top of the stack. So now this is 4. Okay. So now we are over here. We just did this. And now what we're going to do next is we're going to pop the topmost element of the stack and store it in R2. So the topmost element of the stack is over here, which is 4. So we store 4 in R2, then we increment the stack pointer back up. So it was over here. So now it's going to be back up here. Okay. Then we're going to do another pop. Pop R1, store the topmost value in the stack onto R1. So to do that, we see the value here at the top of the stack and we put it in R1, which is 1. Then we increment the stack pointer. So now the stack pointer is back where it originally was. So now after that, we simply print R2. R2 is 4. And then after that, we print R1, which is 1. And then after that, we halt. So our output, our print output should be 2, 4, and 1. Okay, and the values in our registers should have 4 in R0, 1 in R1, and 4 in R2. Any questions on what this program is supposed to be doing before we code this up? Okay, so let's go ahead and code this up. Let me put this over here. Actually, no, you guys probably can't read. Let's just put it over here. So we're gonna need to implement push and pop. So push is gonna be over here, pop is gonna be right here. So let's go ahead and get the machine code for that using the spec. So if I just Command F, push, this should hopefully, you can see that the machine code for push is this. So I'm gonna go ahead and copy paste that here. And we're gonna do the same thing for pop. Pop, the machine code is this. Cool, so now we have the machine codes for the instructions that we need to implement. So let's go ahead and add, let's go ahead and execute and add the if checks to execute these instructions. So if we look over here in execute instruction, we're just gonna go ahead and add an if checks over here. So else if instruction is push, we need to do stuff. Else if the instruction is pop, then we need to do stuff. Okay. So let's go ahead and implement push first. So let's go ahead and write the pseudocode for push. So for push, what we need to do is decrement the stack pointer. Then after that, we need to store the operand, or we need to store the operand in the correct register. Or sorry, we need to store the operand in the stack. What am I doing? Store the operand in the stack. So let's go ahead and do that. So how do I decrement? Let's do some interactive session here. Let's do, how do I decrement the stack pointer? Yes, self.registers, self.stack pointer. Yes. So what I'm gonna do is I'm gonna have, because in our spec, it says that the stack pointer is always going to be register 7. So I'm gonna go ahead and just make a constant here called SP. And I'm just gonna use that constant in my code to reference the register for the stack pointer. So if I'm gonna do self.registers SP minus equals 1. Okay, that is how we decrement the stack pointer. So now to store the operand in the stack, how do I do that? I want to store the operand that I'm given onto the top of the stack. Anyone have any ideas? Cool, let's see, I had an idea. Self.ram write value and register. Value and register, dot self, register, self dot pointer. Yes, so what we basically need to do is we need to do self.ram write, and ram write will take in the value that we need to write to the top of the stack, which is operand A. And the address that we need to write this to is the top of the stack. So that is self.registers SP. So remember, ram write takes in the value first and takes in the address that we want to write it to. The value that we want to write is operand A. And we want to write it to the address stored in the stack pointer register, which is self.registers SP. Okay. And obviously after that, we need to increment our program counter to point to the next instruction. That will be self.pc plus equals 2. Okay. So that is how we implement push. Let's go ahead and implement pop. So pop will take in a register as an operand, and it will take in the topmost element of the stack and put that element onto that in that register. So let's go ahead and do that. So all I need to do, I can do this in one line, self.registers operand A, because remember we are getting a register as our operand. The value of that will be whatever is at the top of the stack. And to get the element at the top of the stack, we do self.ramRead, self.registers, whatever is the address is stored in the stack pointer register. Okay. And after this, we need to increment program counter, which is also going to be 2. Any questions on what we just did for push and pop? Okay, so let's go ahead and run this program and see that it prints 241. Oh, that's a good point. Adam says you have to move the stack pointer. Yes, I forgot to do that. Yes, I need to move it after I've put it in the register. So to do that, let's just go ahead and do that. To do that, we do self.registers sp plus equals 1. So we move it back up. Thank you for pointing that out. Okay. So let's go ahead and run this. This should print 241. So if I run this, ooh, it's not printing the correct ones. So let's go ahead and see why that is. All right, let's see what's happening. Let's see. If the instruction is push, we decrement the stack pointer. That is correct. My stack pointer is 7, which is correct. I store the operand in the stack using RAM write. Solve that RAM write. Operand A onto the stack. No, I don't think this is right, you guys. Can anyone tell me why this is not right? Yes, exactly. Because the operand of push is a register. It's not a value. So what I need to do is, this is actually supposed to be self.registers, operand A. Yep, good. Cool. Let's see if that works now. Cool, and that was it. So now we can see that our program prints 2, 4, and 1, which is what we expected in the output over here. Okay. Any questions on this part of the guided project? As you guys can see, it didn't actually take too many lines of code. It took us probably like less than 12 lines of code or something. Any questions before we move on and talk about subroutines and function calls? Very simple, good, yeah? Cool. All right, so now that we have a good understanding of how the stack works, we're gonna kind of use that understanding to learn about how the computer is able to run subroutines and functions. So let's talk about that now. So what are subroutines and functions exactly? Well, they're basically, I mean, you guys already know what functions are, so I'm not gonna go ahead and explain that. But in order to support functions in programming languages, we need to be able to tell the computer to jump to certain parts in memory and execute instructions, right? And once those instructions are done, we need to tell the computer to jump back where we were originally and keep executing. So let me draw you guys an example just so that you guys can visualize what is happening. So let's just say I have this file called mainfile.py, and this function will have a main function, where your program starts, right? And just any non-trivial program, any non-trivial program is going to have many functions. So we're going to have a lot of function calls over here. And in one line, we're going to have some function called do stuff, right? And do stuff, it could be in the same file. It can be in mainfile.py as well. But in really large, complex applications, it's totally common for this function to be in another library or in another file. So I can have another file .py over here that defines do stuff, and I just import it from main file .py. Right? And then I have my function definition over here. And obviously do stuff can have its own sub-functions as well, and so on and so forth. But now let's kind of think back to what the computer actually does with our programs. Because remember, there is a Python interpreter, and in that interpreter, there's a virtual machine that compiles bytecode into machine code, which are the ones and zeros that are actually executed by the computer. So these two things, you know, goes through the Python interpreter. And the Python interpreter has a virtual machine, and it basically spits out 1, 0, 0, blah, 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 you know, unreadable by humans. But this machine code, this binary code is the code that actually gets executed by the computer. And this high level language that we use is just mainly for us it's mainly for us so that we know how to read it and understand what the program is doing. But in reality, the computer, all it needs are just a bunch of ones and zeros. So now let's think about the memory of the computer. So as what we probably know, we can kind of model the memory as one giant array, and each element in that array will be part of the program that has been compiled. Let's see, unreadable by humans unless you wake up from the matrix. Yes, exactly. So you can imagine that our code will eventually be very similar to what we are doing in our project where, well, I don't have this anymore, but you guys can imagine it'll be very similar to all of these ones and zeros over here. And what happens is you can imagine that, hold on. There's going to be a bunch of these. It's going to be there's going to be a lot of instructions and machine code that will be compiled in a big program. But for example, you can imagine that our main function over here will get compiled down to some certain part of memory, right? Let's just say this main function, when it gets compiled down into machine code, is over here, some part of memory. We can't really know where that is going to be ahead of time. But so the main function gets defined here. And so let's say our program counter is over here and it's now executing the things inside the main function. And, and it's walking through the memory, executing the instructions one by one until it encounters our do stuff function. But the thing is, our do stuff function is in another file. It's not in line with our main function. So it's totally, what's going to happen is when it gets compiled down, the definition of do stuff is going to live in a different part of memory. It's not just going to be over here what we're used to. So we can't just keep incrementing the program counter thinking that we are executing the instructions from do stuff. What the computer has to do is it needs to jump to a different part of memory. Let's say that do stuff is somewhere down here, right? This is where actually the definition of do stuff is, and these are where the instructions live for that function. What the computer needs to do is it needs to basically jump and set the program counter to be here. Because in order to execute do stuff, the program counter needs to be here because that is where it got compiled after the compiler was done compiling our program. So you guys can see that our initial thinking that the program counter just keeps on incrementing down memory is not really, it's not true anymore. What actually happens in a computer is that this program counter jumps to many different parts of memory depending on where that function was compiled and where that function lives. And when we're doing these jumping around, it's very important for us to remember where we were previously. So for example, when we return from our do stuff function, we basically need to, we need to remember where we were over here in main, because we just finished executing do stuff. So we need to jump back to main where we were called so that we can keep executing whatever is in this function, right? So once we set the program counter here and we finish executing, do stuff, right? There's going to be a special instruction for a subroutine called ret, basically signifying that the subroutine is done executing. And once the program counter is here and it executes the ret instruction, it will basically jump back to where it was before, or sorry, it won't be here. It will be here next because we've already finished executing this instruction. So we'll jump over here next, which is the next instruction we need to execute within main. So can someone tell me how, based on what we just talked about in the last lecture, how will we know where to jump after this subroutine has finished executing? How will we know where to jump back to? Yes, we will know it by using the stack, right? So what will happen is, let me first label this. So let me label that this is do stuff, right? This is do stuff handler, right? That's what these instructions mean. So what we're gonna do is, before we jump to wherever the do stuff, wherever we need to jump to, we first need to save the address of the next instruction so that when we're done executing do stuff, we know where to jump to. And we're gonna save that using the stack, right? So remember, we now partition our memory so that there's going to be space for the stack. Let's imagine our stack is over here. Our stack pointer is over here at the top. So what we're gonna do is, and let me make this a little bit more readable. So let me use hex. Let me use hex. Just so that it's a little bit more readable. So let's just say that this is 0x 1, 2. This is 0x 2, 1. Let's just say this is 0x 5, 7. And let's just say, yeah, I think this is fine. Okay, so let's say we're here at address 0x21. We need to jump. This will basically be the call command. So this will be call for do stuff. So this will be a call command. And what we need to do is we need to store the address of the next instruction, which is 0x22. We need to save this instruction because this is where we need to jump back to after we've executed the do stuff handler. So what we're gonna do is we're gonna save 0x22 to the top of the stack. So what we're gonna do is we're gonna decrement the stack pointer, and we are going to store 0x22 over here. So we know where to jump back to. So now what we do is we explicitly set the program counter to wherever this instruction tells us to. So this is basically going to tell us to go to 0x57, and this isn't entirely accurate because there needs to be an operand for that. So this is 0x57 over here. So this call, man, why is my thing? Okay. This call command will take in an operand telling us where to jump. So the operand is 0x57, so we know to jump to this address to execute the subroutine, right? And then after we're done executing that subroutine, we are gonna use the thing that we stored in the stack to jump back where we need to go for the next instruction. So 0x57 over here, so we're gonna jump to 0x57, and then we're gonna keep executing all those commands there until we encounter a ret instruction. And once we encounter a ret instruction, we're going to look at the stack pointer and pop that off the stack and jump to that address. Okay? So that is how call and ret works, and that is how a computer is able to execute subroutines and functions. Does anyone have any questions before I go into the coding portion? And I have a few other slides talking about call and ret. When doing call, will that handler have anything to add to the stack? Yeah, so let's actually talk about those that next. Let's talk about some explicit definitions for call and ret. So call and ret, let me just delete these. So the two instructions we're mainly concerned about is call and ret. So call, it takes in a register and it jumps to the address stored in that register. And it also, but before it jumps to that address, it saves the address of the next instruction onto the stack so it knows where to jump back to after the subroutine is done. So when doing call, will the handler have anything to add onto the stack? Yeah, so it depends. If that handler has another call instruction, then we're going to need to keep adding onto the stack and jumping to that portion of memory. So it's totally possible that a subroutine has a subroutine. If so, then how do we make sure to find the ret address to go back to if another address is added onto the stack afterwards? So as long as you properly execute your call and ret instructions, then it should just work. So let's talk about ret. So ret doesn't take in any operands, but it simply pops the topmost element off of the stack and sets the program counter to its value. That's what it does. It's basically telling the computer, hey, I'm done with my subroutine. Go back to where you previously were and execute the next instruction after this subroutine. Okay. So you have some other slides over here. Yeah, so I think this is just more explanation of call. So call takes in a register and jumps to that address stored in that register. It also saves the address of the next instruction before jumping to that address. So for example, call 0x3 means jump to the address stored in register 3. And to do that, we store the address of the next instruction onto the stack, and then we set the program counter to the address stored in register 3. So let's go over an example. So here's our memory. Let's just say our stack pointer is over here. Our program counter, let's say, is right over here. And it has a bunch of instructions over here. ... And let's just say I have registers over here, which is an array. 1, 2, 3, 4, 5, 6, 7, 8. So let's say that our register 3, 0, 1, 2, 3 has the address 0x, I don't know, FA, just some random address. It doesn't matter. But let's say we are over here and we have the call instruction over here, and the operand that we're given, because remember, call takes in a register as an operand. So let's say that the operand we are given is 3. So when we're executing this instruction, this is basically saying, okay, jump to the address stored in register 3. And in register 3, we look, okay, the address stored in register 3 is 0xFA. Okay, so I'm gonna need to set my program counter to 0xFA. But before I do that, I need to store the address of the next instruction onto the stack. The address of the next instruction is over here, right? This is the address of the next instruction. Let's just say that this is like add or whatever. Let's say that the address of this is, let's just say it's 0x A1 or something, okay? So before we explicitly set the program counter to 0xFA, we need to first save the address of the next instruction, which is 0xA1 onto the stack. So we decrement the stack pointer. We store 0xA1 onto the stack, so we know where to jump back to. Then we set our program counter to the address 0xFA. Then we keep executing that until we encounter a ret instruction, meaning that the subroutine is done executing. And then when we do that, let me move on to the next slide. Ret doesn't take in any operands, and it simply pops the topmost element of the stack and sets the program counter to its value. So let's say over here we encounter a ret command, meaning we're done executing our subroutine. So we simply pop the topmost element of the stack, which is 0xA1. So we set our program counter to 0xA1, and then we increment the stack pointer back up to over here. And that is how we do call and ret. Does anyone have any questions? How do we feel about this? Okay, I see a mind blown one. I see a thumbs up. I see some blank faces. I have a question. Will the handler always take care of any stack items it pushes before the ret? Yes, it should. A correct program should. That's for you guys, assume that it always will. Yes. That's the problem of compiler engineers. Don't worry about that. But the programs that you will run you can assume that. Okay, so let's go ahead and implement this in code. And then hopefully this will give you guys a better idea of call and ret. Okay. Cool. So let me. Okay. So here is the thing that we've been working through in the last few lectures. What we're going to do is we're just simply going to add call and ret, and then we're going to use the stack, the CPU stack, to accomplish that. So we're going to have call over here, ret over here, and to test and make sure that our subroutine instruction is actually working, we are just going to add another instruction called print subroutine instruction over here, which is basically just going to print something so that we know that we are executing the subroutine. Okay, so let's go ahead and do this, and let me just paste this thing so that we have a good example of what is going to happen in our program. So let's imagine our program is like this. We first print high, we save 7 onto register 2, and here we have our first call method, or our instruction. And it's basically saying jump to the address stored in register 2. So what we're going to do is register 2 address, the address stored in register 2 is 7, and 7 is actually here. So what we're going to have to do next is we're going to print the subroutine instruction, which will print some string that we want. And then it will save 500 into register 0. And then after that, we have our ret command, which is basically saying, okay, you're done executing your subroutine. Go back to where go back to where the next instruction is after this subroutine. And the next instruction after that subroutine is to stop the program. So we halt. So our desired behavior is to print high, save 7 into register 2, go execute this subroutine because of this call function, and save 500 in register 0, and then return, which after we execute return, it should stop the program with the halt instruction. So our final state should, our register's final state should have 7 in register 2 and 500 in register 0. Okay, so let's first, before we start coding this up, let's draw up the state of our machine so that we understand what's going on. So our output is going to be over here. Our program is already over here. Let's get a photo of the stack. Here's our stack. Let's just imagine that our program is this over here, right? This will be the program. This part of memory will be the program, okay? And our program counter will start over here. I just want to make sure I visualize the stack for you guys. So first, we print high. Our program counter is here. So we print high. And then after that, our program counter is now over here. Save 7 and 2. So we first need to visualize our registers. One, 2, 3, 4, 5, 6, 7, 8. So save 7 into register 2, 0, 1, 2, which is 7. And then after that, we go to the next instruction, which is call 2. So we jump to the address stored in register 2. But first, before we do that, we need to store the address of the next instruction before we jump to that instruction. The address of the next instruction is this, right? It's PC plus 2, which is halt. So we need to save the address of halt, which let's just say the value of this is it'd be 9. I believe it's 9. Let's just say it's 9. So we're going to store 9 onto the top of the stack, which is over here. We're going to decrement our stack pointer. So now that we've stored it onto the stack, we can now jump to the subroutine instruction. So we explicitly set our program counter to be over here. So you guys can see that if we were to just execute this program instruction after instruction, we would just stop over here. But now, since our program counter is jumping to different parts of memory, that's not really the case anymore. So print subroutine instruction should, I don't know, just say I'm in a subroutine. We'll just make sure that that's running. So we'll print something. I'm in a subroutine. And then it's going to save 500 into register 0. Okay. And then after it does that, our program counter is now over here. It has ret. So ret does not take in any operands, but what it does is it explicitly sets the program counter to the topmost element in the stack. Okay. The topmost element in the stack right now is 9. So we're going to set our program counter back up here to halt, and we're going to pop our stack. I'm going to increment it back up here. And then after that, we execute the next instruction, which is halt. So our program should stop. Any questions on the behavior of this program? I want to make sure that everyone understands what's going on before I code this up. Why was the number stalled by call 9? Shouldn't it have been 6? The PC counter for halt. Yeah, I think probably the exact address is wrong. Let's just see. So the program is 0, 1, 2, 3, 4, 5, 6. Then yeah, yeah, you're right then. I think it should be 6. Yeah, I should have been exact about that. But yeah, it should have been 6 instead of 9. Okay, so let's go ahead and code this up and see that it works. So we have all our instructions over here. Let's just go ahead and add instruction handlers over here. So else if command to execute is push. We'll need to implement that. Else if command to execute is pop. We need to execute that. Else if command to execute equals print subroutine instruction. We'll need to implement that. Yeah. Yes. So for our print subroutine instruction, I'm just going to say, hi, I'm in a subroutine. Okay. Just so that we know it's actually in a subroutine. But what we really care about is push and pop. So push and pop, remember, push, or not push and, what am I saying? Call and ret. Sorry guys, I'm off today. Call and ret. So call, what call should do, takes in a register and stores the value in that register on top of the stack. Oh, yes. Sorry, guys. So it takes in a register and stores the value in that register on top of the stack. So let's go ahead and do that. So it takes in a register, stores the value in that register on top of the stack. Sorry, I'm talking about push. I'm loopy today, guys. I'm sorry. It takes in a register, stores the value in that register on top of the stack. No, it stores the address of the next instruction on top of the stack. And then it jumps to the address stored in that register. Okay, that is what call is supposed to do. Okay, any questions about call? Okay, so let's go ahead and do that. So stores the address of the next instruction on top of the stack. So we need to push the address of the next instruction on top of the stack. So let's do registers, stack pointer register. We need to first decrement the stack pointer. So registers, stack pointer, minus equals 1. And the address of next instruction is equal to what, you guys? What is the address of the next instruction? Is it PC plus 1? Because remember, call takes in one operand, right? PC plus 2, exactly. So address of next instruction is PC plus 2. Okay. So now memory, we need to store this on the stack now. Registers, stack pointer register, is equal to the address of the next instruction. Okay. So now that we've stored it on top of the stack so we know where to come back to, we now jump to the address stored in the register that we have been given. So register to get address from is equal to memory PC plus 1, right? This will be the operand that we are given. So now that we have that, we basically look into that register to know what address to jump to. So let's just do PC is equal to registers, register to get address from. And that is how we jump to the handler for that subroutine. Remember, we're explicitly setting the program counter for our call instruction so that we can jump to that handler for that subroutine. Any questions on call? Is it program counter? My naming is different from lecture to lecture. So I get used to doing one naming in one lecture, then I get confused in the other lecture. Cool. Let me double check this just to make sure it's right. So we're decrementing the stack pointer. The address of the next instruction is program counter plus 2. And we're storing that in onto the top of the stack. And then after that, we're going to be jumping to the program counter specified in that register. So register to get address from is the operand that we are given, memory program counter plus 1. And we explicitly set our program counter to be whatever is stored in that register. Okay. All right, so let's go ahead and implement ret now. So ret does not take in any operands, but it takes the top element of the stack and sets the program counter to it. Okay, so doesn't take in any operands, pops the topmost element of the stack and sets the program counter to it. So let's go ahead and do that. So let's do popping the topmost element of the stack. How do I do that? We did this in the last lecture. Or we just did it today, actually. Memory registers SP, yes. So before we actually pop it, we should probably set the program counter to it first. So we want to set the program counter to the topmost element of the stack and pop it. Okay, so program counter is equal to whatever is at the top of the stack, which is memory registers stack pointer register, right? We're going to explicitly set the program counter to whatever is at the top of the stack, and we are going to pop that off of the stack. So it'll be memory, it'll be registers plus equals 1. Okay. And then that is actually it. Any questions on ret? So let's go ahead and run this. So our output should be hi, I'm in a subroutine, and it should stop. Ooh, that's not good. It says I'm in a subroutine all, so it's looping. Oh, that's because we don't increment our program counter. Let's give that a shot. Here you go. So it says, hi, I'm in a subroutine, and I print our registers, and our registers are correct. This is actually correct because I forgot the last register is for the stack pointer. But it has 500, 0, and 7, which is what we care about. And yeah, so you guys can see how we are now explicitly setting the program counter, and we're jumping to different parts of memory instead of just sequentially executing them. Let me see. I want to get a pulse from people. All right. Good. I see some thumbs up. How do you guys feel about this? It's basically building on top of push and pop. But once you get a hang of it, it's actually not too hard, not too bad. So what you guys will do is basically, you guys will just take this and implement it in your project, just like what you guys have been doing previously. And I don't think that should be too hard. I think the main, once you realize how call and ret are using push and pop, then it's actually not too bad after that. But yeah, it might be a little tricky to understand at first, but just run through a few, just do what we did is kind of just trace what the state of the program looks like and trace where the program counter is and what the state of the stack is, and you guys should be able to get it. Cool. I think right now is a good time for a break. Let's take a 10-minute break. Let's resume at 7:40, and then we'll talk about interrupts for a bit, and then that will be class. Okay? So let's resume at 7:40, then we'll talk about interrupts. And if you have any questions outside of computer architecture, feel free to unmute yourself or post in the chat. I have a question. Do I ever use Facebook dating? Not other than testing. I have a girlfriend, so I don't think she would appreciate me if I use that product in real life. But other than testing, no, I do not. Testing, yes. No, I really just choose it to test. It's a yeah. I get that question a lot from people. Uh, yeah. So we have a rule at work. We can't use that product to date coworkers. So it is a rule, and people definitely do not use it to date each other. I have another question. Is this our final lecture with you? No, it's not. You guys are stuck with me, I think, for 2 more weeks. We have build week after this, which my focus for those next 2 weeks will be hammering you guys with whiteboarding questions and more programming skills. So I'll be talking about common patterns that you see in whiteboarding problems, and I'll be teaching that to you guys. And we'll even do get into advanced topics like dynamic programming and backtracking, um, which will be very interesting. I have a question. Yeah, what do I think about the FTC lawsuits against Facebook? I'm not allowed to really talk about that. Um, I don't. My gut reaction is like that is my gut reaction. That's all I'm gonna say because we are not supposed to talk about that outside of our legal team. But yeah, that's all I'm gonna say about that. Is Build going to be around computer architecture or strictly coding interview stuff? It will be strictly, my lectures will strictly be about coding interview stuff and preparing for them. Yeah, so it's more interview related stuff. We're not really going to be talking about computer architecture anymore after this lecture. How is PC5 gaming going? I did not order a PS5. I don't think I'm going to be able to use it to justify how much it is. I'm hoping my brother gets it because he's really into gaming, and I will just mooch off of him when I go back home and play it there. But I don't think he's able to get it. I only know of one person in my social circle that was able to get one. Everyone else could not get one. PC gaming? No, I used to game a lot when I was younger. I used to play a lot of MMORPGs, and I have sunk an embarrassingly large amount of time in MMORPGs. And I feel like I've depleted my interest in gaming because of that. I've sunk in hundreds of hours in RPGs that my older self kind of has gotten tired of gaming. I'm not as big of a gamer as I used to be anymore. I do have just my trusty PS4, which I've been playing Horizon Zero Dawn, but even then, I can barely play for more than an hour now until my head starts hurting. So I mainly use my PS4 for Netflix or Hulu now, or Disney Plus to watch The Mandalorian. Yeah, MMORPGs are amazing. They are a huge time commitment. Am I being stingy for waiting for the end of Mandalorian season before I resubscribe? No, I think that's actually a smart move. I didn't realize that they were not like Netflix where they release all the episodes at once. They get you because for me at least I fell for it because since I didn't realize that I subscribed to Disney Plus, but they only uploaded up to episode 4. So I have to subscribe for what 1 or 2 more months in order to finish the season. Have I known that, then I wouldn't have resubscribed until I knew they uploaded all the episodes. So I could have binge watched it in like a few days. That is, yeah, it does keep you hooked. It's good for revenue. Lion King. I actually just watched, speaking of Disney Plus, I watched Mulan last weekend. How did you guys feel about Mulan? Did anyone here watch Mulan? How do you guys feel? Man? Eh. Okay, looks like yeah, it's the thing with Mulan I found was I was so into the animated movie that I was just comparing the live action movie to the animated movie. And I feel like if you didn't watch the animated movie and only saw the movie itself, it would have been an okay movie, I feel like. But if you watched the animated movie and you were a kid and you really loved it, then I don't it was eh. It's a good question. Anyone here has not seen Mulan the animated movie? No Mushu, right? No Shang, no Mushu. Yeah. No cricket. It was a spider. Oh, Death Note. Oh, I need to. I should consider watching the live action for Death Note. I didn't, but maybe I shouldn't since people was saying I really bad. No, don't. Okay. Okay. Enough. Enough. Well, let's go ahead and get started again. Let me share my screen. All right. So let's talk about interrupts. So interrupts are going to be a stretch goal for you guys. If you got a really good handle of this, I encourage you guys to try out the stretch goals. I wouldn't say they're the easiest stretch goals because they are stretch goals. They're not really that trivial, but if you guys feel like going for the stretch goals, please feel free to. And I'm going to talk about some of the things at a high level so that that can help you if you do decide to implement the stretch goal. But let's talk about interrupts. So an interrupt is basically a way for the CPU to handle external events. So for example, if you're running a program in your computer while you're using the computer, an interrupt is, for example, you moving your mouse, you typing on the keyboard, or any external events outside of your program that the computer needs to handle. So that is what interrupts are. In your project, interrupts can be called internally via the int instruction. So if we look at the spec over here, here is the instruction. It takes in a register. So it issues the interrupt number stored in a given register. And you will set some bit in one of your registers when you are processing an interrupt. So that is what your interrupt instruction should do. But I'm going to talk at a high level more about what interrupts are and how they kind of fit in with what we just talked about. So during an interrupt, the CPU jumps to execute the subroutines and instructions provided by an interrupt handler. So similar to how we have handlers for our subroutines and handlers for our actual instructions, interrupts also have their own handlers. And the job of the computer is when it's processing or when it gets interrupted by an external event, it's supposed to save everything, save all the states of your registers, put it on the stack, and then jump your program counter to the interrupt handler so that it can execute the interrupt. So a CPU uses a couple of registers to determine, what interrupts are actually enabled and what the computer should care about. One of it is called the interrupt mask. It's a special register which controls which interrupts should be handled. And you have another register, which is the interrupt status, which basically keeps track of the issues or which keeps track of which interrupts have been issued. So interrupts, the interrupt mask is what should be handled, and interrupt status is what interrupts have been issued, because not all interrupts that have been issued necessarily need to be handled by the program. Okay, so for example, if your register has 1, 2, 3, 4, 5, 6, 7, 8. If your interrupt mask is equal to 0B011000001, this is basically saying you care about this interrupt over here, interrupt 1, you care about interrupt 2, and you care about interrupt 7. You don't care about all the other interrupts. So that is what that means. Interrupt status is keeping track of which interrupts have been issued. So for example, if your interrupt status is 0B10001234567, if your interrupt status is this, then this is basically saying while your program was running, interrupt 0 was issued and interrupt 7 was issued. But since your interrupt mask doesn't have interrupt 0 enabled, you don't care about executing interrupt 0. You only care about executing interrupt 7. Because remember, when we did bit masking, what would happen is the program would bitwise end this. And since this is 0, you don't need to interrupt, or you don't need to handle interrupt 0, but 1 and 1 is equal to 1. So that means you need to handle interrupt 7. And there's more instructions on this in the spec if you choose to do the stretch goal, but I'm just giving you guys a high level overview of the registers that are being used when doing interrupts. And also a CPU. So now we've talked about the two main registers that you need to know for interrupts. And let's talk about the next thing is interrupts will also slightly change the memory layout of your program. So remember, we first started out thinking that our program is consisting of just instructions and operands. Then we moved on to saying, okay, now our memory is segmented into different parts for the stack and the program. But now with interrupts, we're adding on another segment in our memory, which is basically storing the addresses of the interrupt handlers. So now our memory, remember, when we first started out, we were like, okay, our memory consists of the program, that's it. But then after our second or third lecture, we were like, okay, well now our memory consists of the stack and the program. But now what I'm saying is, okay, now our memory consists of another portion reserved for the interrupt handlers, right? So For example, 0x00 will contain the address of the interrupt handler for interrupt 0. 0x01 will contain the address of the interrupt 1 handler, and 0x02 will contain the address of the interrupt handler for interrupt 2, so on and so forth. But there's a table here reserved for a vector table. This is called a vector table because it maps from the interrupt number to the address of its handler. So that is called a vector table. And this is specified in your spec. But now know that there's going to be a special portion in memory reserved for the vector table for your interrupts, right? So for example, if the address here is 0xFE, then this is basically saying the interrupt handler for interrupt 0 lives in memory address 0xFE. And for example, if I have this one, 0xAB, this is saying the interrupt handler for interrupt 1 lives in 0xAB, the address 0xAB, okay? So what will happen is whenever an interrupt gets issued and you're handling that interrupt, you're basically going to set your program counter to whatever the vector table says it to be. So for example, if you're handling interrupt 1, you're going to set your program counter to 0xAB, and then you're going to then you're going to execute those instructions starting from that address until the interrupt handler is done executing. Any questions so far? Okay, so let's talk about the things that happens during an interrupt. So during an interrupt, it's going to be very similar to what we just did with call and ret, but with something's added. So during an interrupt, the values in your registers are stored onto the stack, right? So in call, what we're doing is we're storing the address of the next instruction onto the stack. But when we're handling an interrupt, we're going to be saving the values of all the registers and the next instruction onto the stack, because we don't know what the interrupt handler is going to do to those registers, right? It might overwrite the values in those registers. We don't know. So just to be safe, we're going to store the values in those in the registers onto the stack, and then we're going to put them back into those registers after we've done executing the interrupt handler. Okay, so now we've stored all the values in the registers and stored them into the stack. We're going to look at, in the vector table, where we should set our program counter to. So for example, if we're handling interrupt 1, we're going to have to set our program counter to wherever 0xAB is. So it could be some portion in memory, right? So we set our program counter over here. Okay, so that's what we do to the program counter. So after an interrupt finishes, similar to the ret command, an interrupt uses the iret command. I probably stands for interrupt. And what it does is it pops the register values off of the stack because, we've saved them when we're handling an interrupt. We pop them off of the stack and we set the program counter to the correct instruction, similar to what we do with call and ret. The main difference is instead of just storing the address of the next instruction, we're also storing all the values in the register. Yeah, that's the only additional thing we're doing. And if you guys are looking to do interrupts in your project, look at the interrupt section. That's very useful. And also look at the memory layout. I believe that is right here. So here is kind of similar to this. Here's the vector table that maps to the address of the interrupt handlers. But yeah, that is at a high level what interrupts are. For your stretch goal, if you want, you can implement the timer and keyboard interrupt. So for example, you can implement the timer interrupt, which every second should be issuing an interrupt to your program, and you should be handling those interrupts. And another interrupt that you can implement if you decide to is basically interrupting your program when you tap on a certain key in your keyboard. And I will, just as a word of caution, definitely put this as the last thing on your plate. This is definitely a stretch goal. We don't expect everyone to do this. That's why it's a stretch goal. This is not that trivial. Also, I didn't really give you guys a lot of any code to work off of. So it's not going to be as trivial as what we've done in the past. Okay. So does anyone have any questions about interrupts? That's actually all I have for tonight before I end our last lecture on computer architecture. Yeah. Cool. So you guys, I think, are set up for success to implement call and ret. I will post the code snippets we did tonight. Remember, I will have an AMA tomorrow. It's totally optional. Please be there on time. Let's see, I have some question. My question is not related to the lesson, but about build week. Okay, let me see how well I can answer that question about build week. Yes, there will be a 2-week break because of the holidays. I believe we will be able to get through 1 week of build week before we go on break for 2 weeks. Then we end up finishing the second portion of build week in January when we get back. Yes, I think that is the schedule. All right. So that's all I have for tonight. I will post code snippets after literally when I sign off. So you guys, good luck on your sprint challenge. The only hint I will give you for your sprint challenge is get to know your project really well. That's the only hint I'm going to give you for your sprint challenge. So I will see you tomorrow. If not tomorrow, then I will see you guys next week for the first lecture on build week. Okay? So good night.